Okay, everybody, I'm going to work a 3-point cross problem here. I've called up the exam from last year, and as you can see, it lays out a genetic mapping problem with the Zerg from StarCraft. So I'm just going to switch over to a brush that can let me write on this, and we'll get going. Alright, so the way that these problems almost always work is they set up 3 loci in a test cross, and you are going to need to calculate the genetic distances between the loci and draw a genetic map. And the test cross is outlined here. So this right here is the triply homozygous recessive individual that makes it a test cross, and this is a triple heterozygote. Okay, and one of the things you're going to have to do on all of these problems is map the alleles to the phenotypes, and there's a variety of different ways you can do that. I'll just do it the way that makes sense to me, but there's nothing magical about it. You definitely don't want to make a mistake here and be careless. So we've got a gargantuan mutant and a wild type allele that is the normal body size. Okay, so if you go down here, normal body size is the capital G. What I like to do is actually, and I think I'm going to just knock my brush size down a touch and zoom in here so that it's easier for me to write. Okay, so what I like to do when I lay these problems out is just take it one phenotype at a time. So this first phenotype, it's all in the same column here, and so this will be little g, big, and little. Once again, obligatory apology for bad handwriting. So now we've got burrowing and non-burrowing. So if you go back up to the problem, you can see burrowing is recessive, little b. I usually try to follow the convention of italicizing the mutant. Dominant, big B allele, no burrowing. Okay, so let's go back down here, no burrowing, dominant, little b, dominant, and so forth. Make sure I did all those correct. Looks good. And then finally we've got the armor locus. Look, I don't even know what we're breeding here. Anyway, looks like we're just breeding generic Zerg. Okay, so armored mutant. A is armored, little a is armored, and the big A we call soft. See, big A, soft. So if we go back down to the list of phenotypes, you can write down the corresponding allele, right? And the key here is to remember that this only works because we've conducted a test cross. Everybody has one of these chromosomes, which means that everybody expresses whatever allele they got from dad here. So, okay, now remember, this is not necessarily the correct gene order. Alright, it's just a list of phenotypic categories. There's usually 8 categories. Here are the data that you are given. And your job is to use these data to map, to create a genetic map for these 3 loci. Okay, so anyway, that's part A. It's not worth any points, but I highly recommend you do this just to keep things straight. Alright, so let's jump down. Identify the non-recombinant progeny using the space to the right of the table. Now, here's the first thing that you absolutely must remember when you're doing a 3-point cross. Non-recombinant progeny are the most common type. They predominate. So what you need to do is go, okay, which are the most common among all of these, right? And you can see 142 and 134, those are the highest numbers. So just, you could just write non-recombinant here, and hopefully, now I've graded some exams, and I know some of you have worse handwriting than me, so anyway, there you go. That's all you have to do for that, non-recombinant. Now we need to identify the double recombinant progeny. Now, non-recombinant progeny are the most common, which means the recombinant individuals are less common, and doubly recombinant individuals are the least common of all. And so you look for the lowest numbers in your data table, and that is the 3 and the 4. So if you just do something like this, you've done that, okay? So there's 4 points. Now, write down the correct gene order. This is the part that gives students the most trouble, I think. You have to convert these phenotypes to the correct gene order. And the thing to remember is that the allele that appears to switch places, switch phases between the non-recombinant and the double recombinant is the allele that's in the middle. Everything else is arbitrary. You can list the genes from left to right or right to left. It doesn't really matter because their distances will remain the same. Okay? So what you need to do is compare non-recombinant genotypes to double recombinant genotypes. And that's why I had you do this part over here. Okay? So let's just pick this one, for example. I'm going to switch to a different color. We're going to pick this one, and I'm going to compare it to this one. It's generally advisable that you compare the two that are the most similar. So I've got big G, big B, little a, and big G, big B, big A. Okay? So this is a non-recombinant. This is a double recombinant. What's different here? Big G, those are the same. Big B, those are the same. Look at this. Big A, little a. That's how we know A is in the middle. Okay? Now, we could do this one here. Let's compare little g, little b, big A, for example. Little g, little b, little a. Once again, the A is different. Okay? So A is in the middle. So that means when we write down the correct gene order, I don't really care what you do, A is in the middle. So I'm just going to do this. However, this is just as correct for the purposes of this exam, or for this question. All right. Now, fill in the blank of the column of the table by writing the genotypes of each phenotypic class. Use the correct gene order. I strongly recommend you use linkage notation. All I really mean here is to write down the genotypes that you wrote here, but in the correct order. Now I'm going to do something that you don't have to do on the test here, but just for the purposes of clarity. Recall that this is a test cross. So everybody gets one of those chromosomes. All right? So just for clarity, I'm going to write that out. Everybody has one of these, because even if there's recombination in that individual, we can't see it with respect to these phenotypes. Okay, like I say, you don't have to do this on the test, but I do find when I'm showing students how to do this, it's easier for them to understand what's going on. So everybody got a chromosome from mom that looks like that. There's no other chromosome she can give them. What they got from dad, however, see I say it's male here, is a different thing entirely. We know what alleles we got from dad because we wrote them down here. Now we just have to write them in the correct order. Okay? So we have to write G, A, B. These are the same alleles, just in the correct order. And so forth. if you go fast at this step, you'll misrecord something and mess it all up. So take your time, make sure you get it correctly, because if you don't, it could cause problems later. Okay, so that's part D done. Now, draw the genetic map and indicate the map distances. And so that's a big piece. One of the things that, again, I recommend that you do that I don't ask you to do for points on the exam, note where the recombinations occurred. Okay? So I'm going to switch colors for you here. And let's start with the double recombinants. We know it's a double recombinant, therefore recombinations must have occurred on either side of the A locus. And we know, because these are non-recombinants, that no recombination occurred to produce these gametes. These ones are a little bit more challenging. These are the single recombinants. And what you want to do is compare them to the non-recombinants. Okay? So here's a non-recombinant up here, right? And you can see that this little a, big B, those are the same, but we've swapped the G's. So the recombination must have taken place there. Okay, and now, okay. I just saw a mistake. I can't believe you guys let me get away with this. Look at what I did here. I was harping on you guys not going too fast, and I screwed this up and put a big B. See that? So, fortunately, I'm using Photoshop, and I can just erase that, and then I'll go back to my brush and draw a sad face. So that should be little g, big A, little b. Alright, so hopefully now this all makes sense and you guys aren't too terribly mad at me. Alright, so now we've got this one, big G, big A, little b. Okay? And there we've got big A, little b, and again the G is out of phase, and so the recombination took place there. Okay? So this one is similar to this one, and this one is similar to this one. Alright? Now, the last set, hopefully I didn't mess this one up either. So, just logically, you can infer that these two must be the recombinations here, but let's make sure I didn't mess up anything. So we've got a non-recombinant, right? That's little g, big A, little b. And here we've got little g, big A, big B. So you see how this B is different? So that means a recombination must have happened here. Okay, so this one is being compared to this one. And then big G, little a, little b. And here we have big G, little a, big B. Okay, so there's the recombinations that happened there. This step actually turns out to be kind of important later on for figuring out which progeny to use in which calculation. Alright, so if we slide down here, draw the genetic map, and indicate the map distances and the units. Okay, so the first thing you want to do is, here's our gene order, G, A, B. So what we want to do is we just want to say, I'm going to calculate the distance from G to A. And to do that, I need to know the recombination frequency between those. And to do that, I need to know the number of recombinant progeny over the total number of progeny. So, where did we see a recombination between G and A? Here. I'm not sure if you can see my cursor, so I'm going to just go here, 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 and here. So the numbers we want to use are 11 plus 13 plus 3 plus 4. Another common mistake that students make is they forget to add the double recombinants in this calculation. And then we divide that by 500. And we get, that's what? That's 24 plus 7, that's 31 over 500, which is equal to, I don't know, I'm going to guess 0.062. But let's get a calculator and figure that out. Okay. Hey, I know. You should remember to bring a calculator to the exam. Okay, just to be sure, 31 divided by 500 equals 0.062. Oh my god, math. Okay. If we multiply that by 100, that equals 6.2 centimorgans. Units are important. Now, I know many of you have sort of asked questions in class like, why do we care about this? Why do I need to know this? I'll never use this. This is actually about the concept of linkage and mapping, and it's about building habits in terms of units and things like that. If you move on in your careers into genomics and bioinformatics, you're going to deal with more complex genetic maps, genome-wide association studies, all of those kinds of things that do have a lot of relevance in medicine and genomics and bioinformatics and all sorts of different disciplines of biology, and this is the foundation for all of it. So this is really fundamental stuff and building habits. It's not like you're going to go out, become a physician, and immediately start doing three-point crosses. All right, next we want to know the distance from A to B. It's exactly the same approach. We need to figure out where did the recombination events happen between A and B. Here and here. See those lines here? And then the doubles. So we're going to go, drop down a little bit here. 101 plus 92 plus 3 plus 4. Remember to use the double recombinants divided by the total. And that equals, if we do the math in our head, that is 193, 196, that's 200, I think, divided by 500. Let's do the math again. 101 plus 92 is 193, plus 3 is 196, plus 4 is 200. And if we do this math in our head, .40 centimorgans, 40.0 technically. All right. Now, we draw the genetic map. G and A are very close together, so I try to draw it sort of to scale. And A and B are quite far apart. And I would put 6.2 centimorgans and 40.0 centimorgans. And then you want to indicate that you understand that map units are additive. And this is 46.2 centimorgans. You do not have to do this math to calculate the distance to be between G and B. That's the point of doing a three-point cross. Okay, so that's the bulk of the question. The last one, I got two choices here when I construct these questions. Rarely do I ask you both of these, but in this one I'm asking, are the alleles in the heterozygous parent in coupling or repulsion? Now if you recall, coupling means that all of the wild-type alleles are on the same chromosome. Repulsion means that there's a mix of wild-type and mutant alleles on the same chromosome. Okay? So what you need to do is you need to go up and look at the non-recombinants. The non-recombinants, right here, are like the parents, right here. Right? And look at the mixture of alleles we have in the non-recombinants. Big G, little a, big B, little g, big A, little b. Okay? That mixture indicates repulsion. So, we go down here. Repulsion. And then you would add something like, I must construct additional pylons because StarCraft. Alright, so I'll zoom out just a little bit. You're going to see a question like this on the exam, and again, this is fundamental skills and conceptual understanding of recombination and the concept of linkage. And you're using that, you're showing me you understand that by mapping 3 genes using data from a cross, a test cross. Okay? So you'll get the data that look like this, and the problem will be largely constructed like this. There'll be some other ridiculous example. Okay, as always, if you've got questions, shoot me a text, or you can tell me what other crazy videos you want that would help you understand the material before the test. Alright, bye.